Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Hunds put forward an empirical rule in 1925. In 1925, on the basis of magnetic measurements. This rule is helpful in determining the electronic configuration of elements. This rule and its name is known as Hund's rule of maximum spin multiplicity. This rule is known as Hund's rule of maximum spin multiplicity. When electron filling occurs in an orbital, each suborbital s, p, x, p, y, p, z, d, x, y is first singly occupied and only after this pairing occurs. According to this rule, each additional electron enters each additional electron enters a new orbital until all the available orbitals of same energy of same energy are singly occupied. According to this rule, each additional electron enters a new orbital until all the available orbitals of same energy are singly occupied. The electrons in the singly occupied orbitals have parallel spins. The electrons in the singly occupied orbitals have parallel spins. Orbitals have singly occupied. The electrons in a singly occupied orbitals have parallel spins. When all the orbitals are singly filled, then only pairing occurs. Pairing begins with the addition of the second electron in S orbital, the fourth in P orbital, the sixth in D orbital, and eighth in F orbital. The repulsive force between electrons is minimum when electrons enter in orbitals of same energy at parallel spins. The filling of electrons in orbital is known as the repulsive force between electrons in minimum. When electrons enter in orbitals of same energy at parallel speed, the fillings of electron in orbital is shown. Number of electrons. Number of electrons. Number of electrons. Number of electrons. Orbitals. Electron distribution in orbital. Electron distribution in orbitals. If number of electron is 1, for s orbital, the electrons enter in the orbitals as like r as 1. If number of electron 2, for s orbital, singly occupied and then reverse occupied, r as 2. If number of electron is 1 for p orbital, then only 1 electron, and px1. If 2 electron in p orbital, then this is I like field px1, py1, and if for p orbital number of electron 3, p orbital, then the number of field as like, and px1, py1, pz1. If number of electron is 4 for p orbital, then electrons fill in the bracket, initially singly filled, and after that pair are px2, py1, pz1. If a number of electron 5 for p electron, then the number of electron filled initially parallel to each other, and after this field downward direction are px2, py2 and pz2. If number of electrons 6 for p orbital, then electron is filled as like initially singly filled, and after that paired are px2, py2 and pz2. Hence, on basis of Hunds rule, the correct electronic configuration of carbon, C6 equal to 1s2, 2s2, 2px1, 2py1, 2pz0, and not 1s2, 2s2, 2px2, 2py0 and 2pz0. It is wrong and this is the right. According to Hunds rule, orbitals are firstly singly filled. According to Hunds rule, according to Hunds rule, orbitals are first singly filled by parallel filled by parallel spin and pairing takes place. Pairing takes place. So the electronic configuration of carbon is given as. So the electronic configuration. So the electronic configuration of carbon is given as set A valid, set A 2s2 2px 2p py and 2pz. Set A valid and the second set B and set A valid and 2s2 2px py pz. Set B invalid. In set A electrons enter singly, hence this valid distribution of electrons according to Hunds rule. In set B electrons pairing occurs leaving empty orbitals. Set B distribution are valid. Set electron pairing occurs leaving empty orbitals of same energy. Hence this distribution is not valid according to Hunds rule. It may noted that both set A and set B distribution are valid according to Pauli exclusion principle, but only A is valid according to Hunds rule. Only according to Hunds rule, the sexual distribution of each electron in an orbital is determined by both Pauli exclusion principle and Hunds rule. Okay, thank you.